so let's start. The last talk is shared by me. It's my great pleasure to introduce Professor Bolthausen. So Professor Bolthausen got his PhD in 1973 from Zürich. And after being associate and full professor in University of Frankfurt and TU Berlin, he was a full professor in University of Zurich from 1990 to 2013. His specialty is probability, of course, and in particular, he is the authority of stochastic analysis motivated by statistical mechanics. He has made essential contributions to various topics, various problems, such as central limit theorem and local large deviation on random fields, Laplace approximations of Markov processes, random walk in random environment, directed polymers, Gaussian free fields, spin glasses, etc., etc. We are happy that he is now visiting RIMS, Kyoto University, for months as a distinguished visiting professor. He's giving a series of lectures. So if they're interested in the second lecture on spin glasses will be held tomorrow. Okay, so today he'll be talking about random polymers.
Thank you very much thank you very much for the invitation to talk here. I'm greatly honored to be here, invited to Kyoto University and the RIM. And also thank you very much for your kind words. Now, yeah, okay, when Busy said that he was here the fourth time, so I counted how many times I have been here, so it's now the seventh time that I'm visiting Japan. So now this random polymers, that's a topic I had been working on and off for many years. 20 years ago I had worked on the topic, and then again and again. And so recently I took it up again, and I will give a little bit of an overview because I expected that there are also non-specialists here, so what is going on, and then to talk about some specific problems where we had made some progress recently together with Frank den Hollander and Alex Opoku. Now, okay, random polymers, okay, there are two words, so that's random and polymers, but actually it's a kind of double randomness. So already the polymers without putting randomness in front of would be a random object. Now, well, what should be a polymer chain? So maybe if you're just look at the simplest model of the polymer chain. Actually, that goes back to Flory. So you would just take, say, a random chain on a lattice. Say you take the d-dimensional as a square lattice or in higher dimensions. Then you just look at paths of length n which don't have any intersections. So now this is okay. I would say the holy grail in probability theory. Whenever something proves something substantial about that in 3 dimensions, this below 40, I would guess he gets the field. So this is much too difficult to discuss, except in high dimensions. There is known a lot about in high dimensions, and of course in 1 dimension it's a very trivial object here. So, but in the interesting 2 and 3 dimensions, and even in dimension 4, these are very difficult objects here. So now a random polymer would then be a polymer which is additionally influenced by random impurities, so which are living on the space. Now, as I said, this is too difficult, and therefore all I'm talking about is what people call directed polymers. So that's a very trivial object here from the start, without putting randomness on it. So you just take a standard random walk in Z or in the d-dimensional space. So that's then you say in space-time it's what people call a directed polymer chain in d+1 dimensions here. So and then okay, you have the distribution of this polymer chain, so which is of course just a distribution of ordinary, say, nearest neighbor random walks. But of course, if you want to can make it more complicated with more complicated distribution of the increments. But if you just stick to the simple situation, because at every point you have then 2D possibilities in dimension D to move on. So the probability distribution is just uniform distribution here on all these paths. So that's just a picture with realizations. Of course, as probably everybody knows, so there is a scaling limit of this random walks, which is then d-dimensional Brownian motion. So that you see that it's already looking like a Brownian motion. Now, okay, the word random polymer would then relate to the fact that you are perturbing this law by a second disorder, the second random mechanism. I'm using the second mechanism. Perhaps you should remember that. So I'm using this P with this boldface. I'm using for the probability space for the probability measure governing this extra randomness here. So that now you see what would be the simplest situation again. So okay, I put that in quotation marks because it turns out that it is really a tremendous complicated object here. Is that if you would put at every time point, so for the polymer, an independent random variable. So for instance, you can take Gaussians, which has some advantages, or okay, you just also can take coin tossing. You just put a random plus minus 1. So for instance, and you do that independently in every time space-time points. And what you are then doing with the measure, you are transforming the path measure for the random walk by the influence of this extra randomness. So in this sense, you are what you are doing is just you are summing overall along the path. You are summing overall all these random objects here, of all these random variables here. And then of course what you are getting is okay, you are getting this random Hamiltonian, which depends on omega. So for every fixed path, and you are just, that's the usual way people are doing that, you are just putting in the exponent. So people, physicists will put a minus here in front, so, but then there are always a lot of minuses around. I started to drop this minus and just take a plus here. So, but now what you see, what is happening is that the path measure, so for the, now if you're looking at the thing for a fixed omega, so you see in a fixed omega, of course, you're having this kind of white noise. So in every space-time point, you are having this either plus minus 1, just coming from coin tossing. And the path is evidently then trying to move along the most positive paths because they are getting higher weights here. So of course, this is not yet the probability distribution. You have to normalize it by this, what people call the partition function, in order to get the probability measure here. So sometimes people call it the quench measure. So because that is for a fixed realization of this randomness here. And then what people are typically interested in, so of course, then in the large n behavior, how does this behave for large n? So for typical realizations of the omega here. So. Is that clear what is going on? So that the model. Okay. Now, this model has now attracted a lot of interest in recent years, so also in the physics community. Okay, I'm just giving a short survey of results. I don't want to go into details of that. It's actually a very difficult model also. So it might be surprising that it is so difficult. So I think the first rigorous result, mathematical rigorous result was in dimension 3 and larger, and there one proves that there is a critical value for this temperature parameter, inverse temperature parameter, and such that if beta is smaller than this critical value, then essentially nothing interesting happens in principle. So it's not totally trivial to prove that. So that it's essentially not influenced by disorder. So what you are getting is that in the limit you are still getting a central limit theorem. You are getting in the limit the Brownian motion, etc. So that was first proved in a complicated paper using multi-scale analysis, etc., by John Imbrie and Tom Spencer in '88, and then shortly afterwards, I had found a very simple proof, and actually also going a little bit farther than that. So, and then it was going on that there are results, very fine results, also by Gomez and Yoshida. So this regime, so the irrelevant disorder regime in high dimension, that's now very well understood here. So what is much less understood is the relevant disorder regime. So if beta is large, and when the disorder becomes relevant. So what turns out is that in every dimension, so if beta is large, and actually if the dimension is 1 or 2 for all positive beta, the model is in a strong disorder regime. Now, what that exactly means is actually not fully understood. So that what should be the case is, okay, what the picture is that this randomness creates a kind of random tunnels. So what you are having, okay, you are having this space-time situation, and of course you're just having this kind of white noise here, but it turns out that of course the path cannot just follow the plus signs, so because then it would have to jump around much too much. So what turns out is, or what seems to turn out is that you create certain tunnels where so the randomness is somehow untypically large, and then the path measure follows relatively closely to these tunnels. So that is, I think, the picture one is having also from physics literature, etc. So then these tunnels should in principle be much larger than square root of n distance at the end, but if you are just fixing the environment, the path should be confined, relatively narrow, so localized within this channel. Now, results of this direction have been obtained. So starting with 2 papers, Carmona and Hu, and then Gomez, Shiga, Yoshida. So Yoshida was at time here. So these were the first results which proved something in this direction here. But there are still many open questions even in dimension 1. So for instance, in dimension 1 there is a predicted mean displacement, which is actually that this distance, typically distance should be of order n to 2/3. That is this famous n to 2/3, but that is proved only in very special cases. So one case was investigated by Kurt Johansen, and there are some other special cases where this could be proved. So this is what Borodin calls integrable probabilities. So there are some very specific models where you can do very specific computations, and then you can prove it. But it is very far from understanding that under just a general situation. For instance, if you are just taking, say the usual square lattice and just plus minus 1, so coin tossing as random environment, it's not known. It's actually not known mathematically that it is bigger than square root of n in that case. So there are really a lot of open problems. Now this has attracted a lot of attention recently. So in Seoul in the math conference, I think there were at least 3-4 talks related to this problem, but because it is supposed to be inside the universality class, which is now called the Kadar-Parisi-Sang universality class, and there are clear predictions also from the physics literature. So there is a lot of work going on. So also with Martin Heyer, who did a rigorous construction of this Kadar-Parisi-Sang equation, which is a nilpost stochastic partial differential equation. So that's but you see the relations of this directed polymer, which is hypothetical, which is believed to be closely related to this KPZ class, is also not rigorously done. So that's a complicated situation. Now there are models which are much okay. I will come now to. I will just mention shortly 2 models. What? Was it a question? No. Okay. models where much more is known is a case where this randomness doesn't depend on time, so it just depends on space. And then, of course, in that case, you see that the randomness just is creating, there are some regions where the omega is larger than in other regions, and then of course, the random walk would prefer to go to these regions. But of course, there are a lot of competing regions, and of course, it may be difficult to reach the most favorite region, etc. So that is also not an easy object, and there has been a lot of work of it, but a lot is known here. So, for instance, one knows, it depends also on the distribution of this randomness, what is happening. So there has been a lot of work by for this situation by Sneedman, Gerner, König, Fukushima here, Joffe, Werenig. So there is a tremendous amount of work on this type of models. So there is also the model which is sometimes called the annealed model, where you quickly integrate out the randomness. So that is in this case also an interesting model, which had begun with the famous celebrated work by Varadan on the Wiener sausage, etc. So I have myself worked a bit on this annealed model, so I had several papers about that. But that's I'm not going into details about this here. So now, if you want to, you see the direct polymer has something which is independent in time. If you want to do something in this direction and to take the most simple model where you have a time dependence, then you would look at something where just one point in space is affected. Now this looks totally trivial, but in the end it had turned out that there are some interesting questions going on. So I will also shortly mention that. Also, I have not worked on that. So you see, you just take the point 0, which is affected. So your random perturbation, so for the path measure of the random walk is just sitting at 0. So, but outside 0, it is just just 0, and in 0, you are just having omega t. To be specific, I just take plus minus 1 symmetric distribution. And then I'm adding an additional parameter. So if h is large, this would mean that you have a better preference to stay there. So. And then, what turns out, what is of course clear in this sense, it is of course a simple model. So the whole space doesn't really count. So what is the only thing which is counting are the return times to 0, because the only action is at 0. So you are only interested in the return times to 0, and that is the distribution of the return times to 0. And then for the standard random walk, that's known, say in one dimension, that the return times to 0 have a probability distribution, which has somehow, it's not rapidly decaying, so it behaves like n to minus 3/2, if n is even here. So, but you can choose a more general return times to 0. So you can just look at this return times to 0 and take an arbitrary probability distribution. So that is actually convenient, because something interesting is going on depending on this exponent which is appearing here. Now, a problem, you see, what is happening is actually that you have a localization delocalization. That's actually not difficult to prove, that you have a localization delocalization property, namely that if this parameter h is large, then you are just essentially attracted to 0. So that's not difficult to prove. And if h is small, then you're essentially not feeling this randomness. So that's simple to see. That there is a critical point which depends also on the temperature parameter. So that if h is bigger than h critical, you are localized, and if h is smaller than h critical, you are not localized here. So it's not localized in the path. What people have been interested in, I mentioned that because it also plays is of some relevance in the model I'm going to talk in more detail, was this question of disorder is relevant. And this has the following meaning. Namely, the question is if this critical value for h is equal to the so-called annealed critical value. Now, what is this annealed critical value? So what you can look at is at this expression that we had before, but you take immediately the expectation here, so over the randomness. and you just take this function to transform the path measure of the random model. Now, that is a trivial object, because if you do the computation, you just see that the randomness which is here is just entering in a totally trivial way. So in the coin tossing example, it's just shifting h by a fixed parameter here. So it's just the same as if you wouldn't have randomness, but would have shifted the h to some larger value. Now, if you are in dimension 1, you then see that for this model you are localized if this is positive, and you are that's just very simple and trivial. So that in dimension 1, for instance, it would be localized if this is positive, and you are delocalized if h is negative. That's just okay. That's just an elementary exercise. But then the people ask the question: gives this also the right critical values? So for the real random model here. So, and then in that case, one would say the disorder is not really relevant, and if you have a different value, there's always an inequality coming from Jensen's inequality. But the question is really if you have equality or not equality here. So and that got some prominence in the physics community, because there were some competing claims about that. What is happening at the value for alpha, which corresponds to the simple one-dimensional random walk, which is where alpha is 3/2. So because there were two groups of people, the one were claiming that the disorder is relevant, and the other that the disorder is irrelevant. So that was finally solved in a complicated paper by I think it was Giacomin, Laguin, and Toninelli, who proved that in the critical case, disorder is relevant. So it had been proved before that if alpha is more than 3/2, and if beta is small, then the disorder is not relevant. And if alpha is bigger than 3/2, the disorder is always relevant here. So this question, that was an interesting problem in this model. So the question if disorder is relevant or disorder is not relevant. Now I'm mainly going to talk about another problem which was introduced, another version, which actually is not so far from this just pinning model I have just explained, but which shows some new features, and actually where there are still some problems which I absolutely don't understand really. So this was introduced by these four physicists in 1989. Okay, they took the name copolymers. I think it's still very active in the physics community. In the physics community, that they are looking at models which are much more complicated than the model I'm explaining here. So there are, okay, a couple of years ago there was a whole conference essentially on this type of models here. So now, okay, what I'm sticking now is to dimension 1, because I have to stick to dimension 1, and then I'm just looking at the following thing, which is maybe, okay, it's the same type of model as we had just encountered before, where the randomness just sits at one point, so in space, but it has, okay, maybe the simplest, okay, space dependence. Namely, I'm taking, again, okay, just coin tossing for this omega t, and I'm adding an additional parameter. That's actually important. So this additional parameter, and then I'm just taking the sign of x here. So then the Hamiltonian is just I'm summing over omega t plus h, and then the sign of the. So if you are on the positive side, you're just counting positive, and otherwise negative. Now that means that if, say, omega t is plus, you can take more general distribution. I'm just sticking here to coin tossing. But that doesn't matter if you restrict here to coin tossing. So if that is +1, of course you have a preference to be on the positive side, and if it is -1, you have a preference to be on the negative side here. So it was introduced by these four physicists in order to have a model for a polymer chain sitting at an interface, where, say, the nodes of the polymer chains are either repellent to one side of the interface or repellent to the other side of the interface here. Now, okay, it's just that's just a formality which is not important. So it's actually slightly more convenient to ask for the bonds than the sides. So I'm just taking the sign of st minus 1 plus st instead of the sign of st. So you see the bond is just then on one side or on the negative side. But that's okay, that's irrelevant. Mathematically, it's slightly more convenient to do it in this way. Okay, I have here a picture, so you should think of an interface, say, between water and oil, and then you're having here your polymer chain. Maybe the blue ones would like to be in the water, and the yellow ones like to be in the oil, and so it's okay. At first, it's not quite clear. You see, essentially, what is more or less evident is that either this changing, this randomly changing attractions either to the watery side or to the oily side is either attracting the polymer chain to the interface or has no effect, or just force the random walk to be on the positive side, for instance. Yes. So you see, I had this asymmetry, which is which will play a big role here. I'm having, so if H is positive, you see the oil attractive side is stronger than the water attracting side here. You can change that. It doesn't matter very much. You can also change the frequency. So, for instance, having more oil repellent or more water repellent than oil repellent. So that's not really important. And then you can look at the Gibbs distribution here, so in the usual way, and then that's just the normalizing constant in order to get the probability distribution. And then one looks at the so-called free energy, which is what is called the quenched free energy. You're looking at it's not it should be the pressure. So the free energy in the physics language would have a beta here below. So, but I'm leaving that out. So you want to look at the almost sure limit here. It's not, in principle, the limit could be a random variable, but it's actually not difficult to prove that it is not. So what is actually happening is that you're having, in all these models, so also in spin glass theory, etc., you typically have the self-averaging property of the free energy. So you can take the expectation outside the logarithm. So I'm just taking the integral over the randomness over the logarithm. You're getting the same limit. So that is a simple consequence of this concentration of measure property. So to have something like that. So it's not difficult to prove that this exists and is non-random here. Now there's a trivial lower bound here. You see, I'm assumed, I had it on one of the last slides here, that I'm assuming that H is non-negative, because if H is negative, it's just symmetric here between the oil and water side. So there is a trivial lower bound, namely you could just look at the random walk which stays positive here. So if the random walk stays positive, of course the sign is always positive, and you're just getting this expression. And by the law of large number, that's of course just the sum over the omega n is of order square root of n. So that doesn't count after you take the logarithm and divide by n. And then you have just in n beta h, and you just what is the probability that you stay positive? That's well known that it is of order 1 divided by square root of n. So that doesn't count after you take the logarithm and divide by n. So you get just a trivial conclusion that this free energy is bigger or equal to beta h. And then you say if it is bigger, then you have the path localizes, and if you have equality, the path delocalizes. Now that's of course a little bit fishy. So because, but in principle, if you think a little bit about it, you see either the path can beat this strategy staying positive, but then it has to hang around zero. So that's actually You have to prove, and it's actually proved that if you have strict inequality here, that was a result by Marek Biskup and Frank den Hollander, that the path localizes in a strong sense, that you have say exponential estimates of the deviation from zero, etc. Now, if you have equality that the path really delocalizes, that's still somewhat nasty. That's known in some region, but there is still an open problem here. But from now on, I think there should be no serious doubt that you have something like that. from now on, I take that as a definition here. So that might look a little bit fishy, but I think it's, I don't think it's an interesting question here. So if it is, how this is really related to that. And then you can ask if is there a critical value here such that, you see, of course, what you expect is that if H is large, so then the positive side gets more attractive. And then of course, okay, you feel that is, okay, the path is more likely just to stay on the positive side on this interface here. So in principle, okay, at first you think, okay, it's not clear that H equals 0 where you have symmetry. The path localizes here. But that was actually the first rigorous result in this direction. So, but anyway, I can define this critical point. So the smallest point where you start to be localized. Okay, where you start to be delocalized in this sense. Now, okay, at first, yeah, maybe I already can mention here the first rigorous result was really this result now 20 years ago by Sinai, who proved that you have localization at H equal to 0. So for all beta. There's no critical, at H equals 0, there's no critical value for beta. It's always localizing here. So that was first proved by Sinai. Now, the next point is that it proves that it's really, if H is large enough, so maybe depending on beta, then it starts to delocalize. And that at first, actually, we first proved that in the paper with Frank and Hollander also some time ago. But that is done by comparison with the so-called annealed free energy. But actually, if you do it naively, then it doesn't work. So you get essentially nothing. So what you have to do is what people call a Morita correction. So we invented that ourselves, and we're very proud because we found this nice trick. Okay, I will explain you. But actually later people told me that yeah, this is a well-known trick. What they are doing here in this context is, you see, the Hamiltonian was just that with that. You are subtracting -1 now. Now this is, of course, something totally trivial. So because if you are subtracting -1, you are just subtracting here the sum over the omega n plus nh. And as I explained before, the sum over omega n doesn't count for the free energy. So you are just subtracting beta times h. So you have a modified free energy, which is just given by that. Now we had before the question if that is bigger than that. So the question is now, is that bigger than 0 or not? So that's now the question. Now here the advantage is that you can do what people call, you can compute the annealed free energy, namely where you take the expectation over randomness inside the logarithm. Now by Jensen's inequality you always get that. So you're getting that is smaller or equal to that. Now what turns out is that this is typically easy to compute, this annealed free energy. And what actually turns out, okay, that's just the back of an envelope computation, that this is 0 as soon as h is bigger or equal to this annealed critical value, which is in the coin tossing example, it's just this expression here. So you see it starts, you see the log cosinus hyperbolicus starts with order beta square, so it starts with beta. So it starts with tangent 1, so this critical line. So you get this annealed critical line, and then because you have this Jensen inequality, you know that the quench critical line is below this annealed critical line. Yeah, so. Now the curious fact is, if you do it on the original model, you don't get the conclusion. So if you do if you compare the free energy in the original model with the annealed free energy in the original model, then you always get strict inequality. So you have to do this Morita correction. So in order to get the conclusion here. So okay. Now that was actually open for some time. If you have really a strict inequality, actually there was some papers in the physics literature first claimed that you have inequality. But actually what is now known, that was in a paper by Doninelli, and it's also contained in our recent paper I have with Franklin Hollander and Alex Opoku is that you always have strict inequality. So in this sense you have always disorder. You have disorder relevance here. So this an critical line is never the correct critical line. Now, you can do the same generalization as above. So namely, instead of having the return times to 0 given by the one which you have from ordinary random walk, you can just take an arbitrary. It's actually interesting only if you have this polynomial decay n to the power minus alpha with some alpha bigger than 1. And then you can just think of, okay, you have this return times to 0, and then you just flip the excursions with probability 1/2. Okay, I want to go a little bit about the history. So I already mentioned this result by Sinai, who proved that you always have localization if beta is bigger than 0. And then there was this paper. Okay, it's now also nearly 20 years ago. I had with Franklin Hollander, where we proved the existence of a non-trivial phase diagram. So we proved that there is a critical line, and actually what we proved that actually the main contribution is first we proved that that there is a tangent and the origin. So you see we had this anneal critical line, which was going like maybe. So this is somehow called annealed. Oh, and we know that there is something below, so something. Okay. In the meantime, one knows that the correct critical line is that should be beta, and that should be h. Okay, and that's h critical of beta. Now, what we proved that it has a non-vanishing tangent at the origin. So what you think, of course, if beta goes to 0, that's a simple perturbation argument, but actually it's not true. So that it's a rather complicated renormalization argument you have to do if beta and h goes to 0. So it was actually a very complicated proof, that you have a tangent at the origin. And I would argue this tangent at the origin is the interesting object here. So because it has some universality properties. So that has, okay, we had it more or less implicit in our paper, but it has in the meantime been proved by Caravena and other people. So namely that the tangent at the origin doesn't depend on the exact nature of the model. So for instance, if you change the distribution of these omegas, you get the same, or if you are changing, okay, the model slightly, by having, say, more of the positive, then you see here we still have half are attractive to the oil side and half are attractive to the watery side. But you can also change the frequency, etc. And this influences the critical line. So the critical line depends on the distribution of this omegas here. But the tangent at the origin depends only on alpha essentially. So on this it turns to 0. And okay, what we proved is that this tangent at the origin is of course smaller than 1, smaller or equal to 1, because it is bounded by this annealed critical line. But we also proved that it's positive. Okay. Yeah, that's the main issue. So the value is that's my big open problem. So that in the community for people that are looking at these random polymers, this is a very interesting problem. So for the rest of my talk, I essentially talk about that problem. So that's now a big progress. Okay, it was actually just. Okay, it was not a very difficult proof. I will give an indication of the proof. Was actually somehow curious result, namely that the critical line here, okay, this critical line is looking the same as an anneal critical line. You remember, so the anneal critical line was just 1 divided by 2 beta, log of 2 beta, and now it's you just replace beta by beta divided by alpha. So then you you should think of alpha being 3/2. So for the ordinary random walk. Yes. Now this gives a bound which gives the kappa alpha is the tangent at the origin. So which gives this is bigger than 2/3. So for the random walk, so 1 divided by alpha and bound above by alpha. Actually, there was a physics conjecture that it was 1 divided by alpha, and that was more or less the belief for some time. So that it is always 1 divided by alpha, so which would be 2/3. So now this was okay for a long time. People were thinking about that this should be the critical value. I think essentially until this was kind of ruled out by a numerical study by these 3 authors in 06. So now they did a numerical study. Now the authors were always carefully about the conclusion for the tangent at the origin because they couldn't really simulate it close to the origin. So they simulated a little bit above. But on the other hand, it was really a good numerical study. It was not this kind of numerical study where you, in the end, don't know if there are additional, finite size effects, and you never know the conclusion. So the numerical study was absolutely fully controlled. So if the number, if the number generator was okay, then with probably 1 up to 99.999%. So the conjecture, actually, Montu's conjecture was that the critical line is really given by this line is not correct. So it was really a fully convincing numerical study here. So now, actually, Giambattista Giacomin showed me a physicist argument which actually modified the conjecture that it is 5/6, so in the random walk case. So I don't know what I should believe. So because we have made some attempts in this direction to prove something like that. But anyway, now then the other results were okay. The open problem was really to mathematically disprove this conjecture that it is 1 divided by alpha, so it is 2/3 here. So. And then actually some considerable progress was made by Fabio Toninelli, who proved actually that this critical line is strictly below the annealed critical line. And actually he also proved that the tangent at the origin is smaller than 1. And then, there was also some progress, but only for larger alpha here about by Bodino, Giacomin, Lacuna, and Toninelli in 08 years. Now we have a new paper it just has appeared, so in the Annals of Probability with Franklin Hollander and Alex Opurku. Now, to summarize, the new results is that we have, a somehow complicated but I think nice variational characterization of the critical line. I will give that here. So now using this variation, the variational characterization is complicated because it uses this what people call this level 3 large deviation principle. So it really uses the heavy machinery of large deviation techniques, and actually we could use it to disprove this Montu's conjecture completely. So we proved that the critical line is always above this Montu's conjectured line, and we could also evaluate it at the tangent at the origin here. So we got some estimates, with some, I call it B alpha, and it is somewhat complicated. It satisfies the complicated expression, but we could prove analytically that it is bigger than 1. So it just disproves this Montu's conjecture for all alphas. So that was a big step. That had been an open problem since 20 years, and I know that a number of people have tried to disprove this Montu's conjecture, or maybe for some time also to prove it. Yes. We also got a new upper bound, which is actually not better than, actually slightly worse than using this variation characterization of this strict inequality between that and that. But I still have considerable hopes that we can improve that using this variation characterization. Now, this variation characterization is somewhat complicated. Now, just recently, a couple of maybe 1-2 months ago, I actually was able, probably Frank wouldn't like it, so to get, I shouldn't have said that, that's reported here. So but anyway, to milk out an elementary proof of the lower bound here. So bypassing essentially this heavy, large aviation machinery. But I have to say that probably it would have been difficult to find it without seeing first the variation characterization. So now I'm explaining that shortly here. So the basic step is I'm starting with the original Bodino-Giacomin proof that the Montus line is a strict lower bound. And actually, no, it's not a strict lower bound, it's a lower bound here. Now the Bodino-Giacomin argument is just actually taking the Montus argument, which is actually a simple argument. So Cecil Montus believed that this gives the correct critical value. But actually the argument she had gives just a lower bound. So that's it. And it is running like that. You are looking at intervals, say, of a certain length, which is for the moment fixed, but in the end it has to go to infinity. So, but take it for fixed for the moment. And then you are looking at, you see we are at the situation where h is positive. So where in principle, on average, okay, it is favorable to be on the positive side. Now how can it be localized? Of course, only if there are some, by randomness, there are some some intervals where the omegas are untypically low. So now you can just look at intervals, say, of length k, where the sum over the omega t is, say, x, which is negative here. And then you are just looking at the successive such intervals. Now, of course, if x is somehow small, or if the interval is large, then they are very rare, so of course. So, but you can just look at the successive such good intervals. So I have, okay, that's a bad picture because of between here you of course have randomness, but I'm not able to do it on the computer. So just I have symbolically made this smooth curves which should represent the random walk. So these red parts are the good intervals where the sum over the omega is small. And then you're just saying, okay, what the path could do. I'm just estimating that by restricting my paths to, okay, it's really extremely simple. So just staying positive all the time, then coming down to 0 here at the end point of this interval, then on this side being negative, and then being positive, and then negative again, etc. You are doing that, which is extremely simple-minded here. So and then you let n go to infinity. Finally, the length of the intervals going to infinity, and you optimize over x, and you do the computation. It's not a difficult computation here. So then you get that as soon as h is more than this value here, then this Morita modified free energy is positive. So then you have proved that the critical value is above that. Now if you I had been thinking and discussing with Giambattista Giacomin many times and with Thierry Bodino, and in principle, okay, you can start to modify a little bit and maybe say you're getting a little bit of entropy by not going down every time, etc. And but if you do the computation, you see you gain nothing. So in this way. So on the other hand, it's not clear if you can really do something better. And obviously, Cecil Montus somehow believed that you cannot do better than just looking at stretches where, say, on average, the omegas are say untypically negative here. So that is people were just switching forth and back all the time what to think about here. Now I show you what the improvement is. So this improvement was coming out from this infinite dimensional variational formula, but then just contracted down to something which is elementary. So the improvement is, okay, sorry. I'm looking at the set of finite length plus minus 1 sequences here. So these I'm calling words. So I'm just having an alphabet which is plus minus 1, just 2 letters, and then I'm looking at finite such sequences. I'm looking at such words. And okay, if I have such a word, the length I call L, and sigma is just the sum over the xi's. Now, I'm fixing finitely many such words. So maybe just, in the end, I have to take infinitely many, but okay, I'm just fixing finitely many. So 3 Kyoto is beautiful, so something like that, 3 words. And then I'm fixing numbers here, n1, n2, up to nm. So for instance, 50 times Kyoto, 30 times is, and 20 times beautiful. And then I'm looking at all sentences I can make with these 3 words, taking 50 times Kyoto, etc. So that's, and then I'm taking, so equal distribution on all the sentences I can make. So with 50 times Kyoto, 20 times is, or 30 times beautiful. So of course, the number of such sentences is a binomial factor here. So I'm just taking equal distribution on that. Now, what I can do is just I concatenate these sequences, and then I'm just getting a plus minus 1 sequence of this length here. So if I concatenate it, this doesn't work with the Japanese characters. But plus minus 1, okay, you can do it. So then you are just getting, what you are getting is a probability distribution. You're starting with this uniform distribution I had before, and then you're getting a probability distribution on these sequences of minus 1, 1. So I call this probability distribution gamma. Yes. So now, the important point is that you can get the same sequences of plus minus 1 after concatenating by, of course, different sentences. So now what I need is that there's a kind of equipartition property, namely that, actually I couldn't quite prove that. It's slightly wrong what I'm writing here, so I had to smear it out. Probably somebody here tells me that is well known, etc. So this equipartition property, but when sitting down, I had difficulties to prove it in this form. Also, it is the essence of the argument here, so I had to do some a little bit smoothing in order to get it. So it says that in the limit where you let these numbers go to infinity, and so the relative numbers go to some pj, which is supposed to be positive. I haven't written it here. So then the following should be true, namely that you have a set essentially of full measure under this gamma, such that for every sequence of x, you can find the number of, say, nx of sentences you had before, which are mapped to this point x, that they are all essentially equal. So that you have this equipartition property. So actually in this form I had difficulty to prove it. Also I believe it is correct. But I had to somehow smear the distribution a little bit out. So now the rest is just a modification of the argument I had before. So I again look at these good intervals. These good intervals are the intervals where the sequences is in A. So they have length L, of course. And so that is omega restricted to this interval is in A, in this good set here. So. And then what you are doing is that between the intervals you stay positive. So with the random walk. But if you encounter such a good interval, now you have to do still a lot of possibility to split. So you split that into these n possibilities to get the sentence as I described before. So of this finite number of words, and then inside this interval, I let the random walk just come down to 0 at the end of these words. So I have maybe I make a picture here. So I just. Okay, I have one of these good intervals. Okay, and then I have many ways to divide it in these words. And then my random walk comes down to 0, and I still flip it to plus minus 1 with probability 1/2. So I just look like that, maybe that, and then that. But you see, I have many possibilities. I had these n possibilities to do this splitting. So I'm doing that then I'm getting a lower bound for this sum by looking at all this possibility here. So, and actually, it's very important. It's very important to have this. This is doing all the job, that you have many possibilities here. That is giving you some entropical gains. So now, if you finally you optimize over m and this pj's, so and let n go to infinity. So pj was the relative proportion of word j in this collection. So, and what you are getting is the following criterion. Okay, you just have to make it out. Okay, it takes a little bit of efforts to do the computation. Is that if there exists a probability distribution on the set of words here, which has the probability, which has the property that the integration of this expression log of that with respect to mu is bigger than alpha times, okay, what is relative entropy between the measure mu and this measure here. Now this measure here is what you are just taking. Rho was the distribution of the return times to 0 under the random walk, say. And you are just taking the length of the word distributed according to this return times to 0, and then just flipping coins with probability 1, just with coin tossing. You're just looking at this relative entropy, and if you can satisfy this inequality, then you are in the localized regime. So you see what is happening here. You have this expression here. Actually, it's not a mysterious, this expression here. It's just computing. You see with probability, if you take the sign with probability 1/2, you arrive at positive. But after this Morista correction, you get nothing. So because I have subtracted this one. Yeah, so, and if you are on the negative side, you get this. So it's just okay. That is no mysterious this expression. Now you see, of course, you see this expression is always positive here. Now, if this is smaller than 1, if this would be smaller than 1, of course you cannot satisfy that. So and then you see that this part is always, you see this minus 2 beta h times the length. That's of course always negative. So that's bad. So in order to beat that, you really have to. Is there a sign wrong? So no, it's okay. So you see the sum over the omega i's have to be negative in order to really beat that here. So you really have to find a probability measure where there are many which is concentrating on words, wherein typically, of course, this sum is negative here. And after you have reached this stage, the rest is routine. So because then you can optimize over mu, and it's actually easy to see what the optimum mu is. And then okay, there are some computations to do, but in the end you are getting this property out. So this finally disproved this Montus correction. So it was okay. We were quite happy that we could find it here. So now. Okay, I see. Now I have to. I wanted really to explain you also the variation formula. Okay. Can I do that in 2 minutes? I have 10 seconds to think about it. Okay, maybe I quickly do it so that you see it's really complicated. So it's actually based on a relatively recent large deviation principle by Birkner, Greven, and Hollander. I want to explain it a little bit, but I have to be a little quick. Now, just to see how complicated it is. So what you have to look at is you look at the set of stationary probability measures on this infinite product space on words. So W were the words, so this finite length plus minus 1 sequence. Now, okay, the average length under the probability distribution I call as MQ, and then if this average length is finite, I can use that, can use this concatenation mapping, which is, okay, mapping this set into the set of -1,1 sequences, infinite length -1,1 sequences through concatenation. Now, I want to get an invariant probability distribution. Now, if you start with an invariant probability distribution here, you don't necessarily get after concatenation an invariant probability distribution, but you can somehow average a little bit, and you can produce an invariant probability distribution. So I'm not going to detail how to do that here. So again, I'm having also this probability distribution on the set of words, which are just coming from where you choose the length by this distribution of the return times to 0 and coin tossing here. So now, what the theorem we have, this is now giving really an variational characterization of the critical line. But you see it's not very explicit here. Is that h is smaller than this critical value if and only the following expression is positive here. And this expression is, now you have to take the supremum over all probability, invariant probability distribution on this infinite product space here. So now what you do is the first expression is just a relatively simple object here. So you're just taking the first, you see you're just taking the first marginal on the first word and look at the integral over that. So, but then you have to look at this specific relative entropy of this Q with respect to the infinite product measure of the small q, which is given by the limit where you look at the marginals of the first n components of the usual relative entropy, and then you divide by n. So this is called the specific relative entropy. And then you have just to subtract here also alpha minus 1. You should also always think of alpha being 3/2, and then the mean length. And then you also have to have the relative entropy after this concatenation with respect to coin tossing here. So that's, no, but you can imagine that this is somehow difficult to evaluate. So when we found it, we were proud that we could find this lower bound, but as I explained, in the end you can work out the same lower bound, but just by doing it in an elementary way. But we could also use it to derive an upper bound and get the strict inequality for the upper bound, which is at the moment not perfect. Because for sometimes we thought that we could get this alpha 1 divided by 2 alpha as an upper bound from this variation formula, which would give this 5, 6, so this new conjecture. But in the end, it was based on a long computation which involved some interchange of limits, but we finally realized that this interchange of limit is not okay. So for the moment, but okay, it's we still have the hope that we can make out something better from this variation formula with regard to the upper bound. No, I should say I don't know if I should really believe in this 5, 6. At the moment, this question of this tangent at origin, maybe it's not an interesting question in the end. So maybe it's just a complicated object. And so what we never managed to do is directly get the variation formula for the tangent at the origin. So that's also a drawback or a shortcoming we have at the moment here. At the moment, I don't know if you should expect, say, a nice structure. Of the optimal choice of this Q, if you are, say, close with beta and h to 0, and if you are close to the critical line. So my suspicion also, it's partly influenced by looking at the simulation, is that there is a nice structure. So namely that the random environment, when you come down to 0, so in the localized regime, if you are close to the critical line, has a kind of multi-fractal structure. So it could be that it has a nice structure. And then you could hope that you get something interesting out of it. But it could also be that it is in principle not very interesting. So you just have an arbitrary optimizer which you cannot really nicely characterize, and where you cannot draw any say specific conclusion what the tangent should be. So it's just some number which is not an interesting number. So that's the situation. So we see we made some progress. But we have not solved the problem. But maybe the problem is uninteresting. So at the moment I don't know. Okay, thank you and.
Thank you very much. Questions?
I have a question about the model. I mean, why we do this particular model? Or I don't know. If we think of this polymer chain, one way to think of it, I could imagine, is that it's kind of created, right? And so we throw in material and it's getting longer and longer in a random way. But now you kind of weigh not the process of making it, but the whole polymer with this randomness. Is this the same as the way I described it, where you somehow would kind of cross the set way?
Where it is growing. So yeah, it's actually a good question because also say just with these non-random things there are two. So for instance, if you are just looking at polymer chains, so not random, not influenced by random impurities. The standard way you are doing it is that you fix the length and then you just take uniform distribution over all paths which have no self-intersection. So this gives you one measure. So another measure is where you produce it dynamically. So that means that you go step by step, and you just always go to points which you don't have visited. So now this is not a good model because you can create traps and then you got caught into traps. But you can make it a little bit soft. So you're going on, and then you're making your jump according to the number of times you have already visited, and you punish if you have visited that. Now this is okay. You might think that it has similarities, but it is completely different models. So for instance, this standard model where you fix the length and take uniform distribution, this is known to be diffusive, starting with dimension 5, and actually with borderline case in dimension 4. Now this is a proof fact in high dimension. So that's and 4 dimension. I think it's going on since I think it's more or less proved. So that's kind of proved. So that's the situation. Now this model where you just go dynamically on and avoid points where you already have been. This was called truly self-awarding work by Parisi and the group. So now this should have critical dimension 2. So this should be diffusive in dimension 3 and larger, but it's actually not the proof fact. There are some results in this direction by Ball and Todd. So these models are different. So actually in physics, so it's typically, of course, what you would like to have is, okay, this is just beyond. If you go to physics conference, of course, they are doing that. So you're just taking, say, a 3-dimensional polymer chain of a length, and they say, okay, there's some randomness on it, and part is attracted to the positive side, part is attracted to the negative side, and you have just oil and water, and you just put it, is it localized, is it sticks to the surface or not? But of course, 3-dimensional self-awarding work, nobody can do. So this is a problem for the next century. So that's just beyond reach. So nobody, for instance, to tell you the knowledge one has about 3-dimensional self-awarding work in 3 dimensions, it's not known that it is not space. It's crazy. So it's not known that it is not space filling. So you, of course, if it is self-awarding, it has to fill at least endpoints. And then if it would be confined to a ball, it would essentially have distance n to 1/3. So because endpoints, you need a ball of radius n to 1/3. It's not known that this is the situation. It's not known that it is diffusive, so that the end-to-end distance is mathematically. Of course, the physicists know that the end-to-end distance is n to 1.58 something or something like that. So, but this self-awarding that would be the real problem. So to look really at the real, that would be the physical relevant things. So, but that mathematically, that's just beyond.
In the last part, you mentioned that you tried to have a more quantitative upper bound, but to include because of the extent. So do you say it disproves this conjecture, or I didn't catch that?
Yeah, the lower bound disproves the conjecture. Disproves the
upper bound. If you could prove this upper bound, quantitative upper bound you mentioned.
Yeah, we had hoped, actually we still hope that we can do this, prove the tangent alpha plus 1 to 2 alpha. Actually, the situation is that in order to milk out, okay, it's difficult to milk anything out so directly from this variation formula. So you have to use estimates on these entropies. So you're doing some estimates on these entropies. And then we did these estimates, and actually this proved that the anneal critical line is strictly above. So we could do that. No, actually not this. That was a sore point of our argument, that we couldn't do the slope. So we did some computation, was a somewhat lengthy computation, and we got out by the interchanging this limit that we got an upper bound alpha plus 1 divided by 2 alpha, and we were totally happy. But then there was this question of interchanging the limit, and actually we could prove that actually this is not justified, and if you do it, you just get 1. So in this way. But actually, the construction of the example where you really prove that it is only gives 1 is done in such a way that you think it could be ruled out from the original. So variation formula. We still hope that thinking a little bit more, you see, and using really the variation formula in its true form, that we could get. But that's. We have not worked on it for some time after this disappointment, but we certainly want to take that up. So.
In this new conjecture of 1 plus alpha divided by 2 alpha, what kind of intuition is it?
Yeah, I cannot tell. So Giambattista, it's very fishy. So the physics argument, but then I even cannot clearly remember how it was going. So. Was just mentioned once by me by Giambattista Giacomin, but then actually the simulation totally fit with this. So it could well be that it is true. Now, if we really would get the upper bound, then I think we would have much better intuition. So for that, I must say I'm somehow. Originally, I was very doubtful that a simple value should do the job, but I think one should really understand. Okay, one should understand what is happening if you are approaching the model, say, from the localized, say, to the critical line. So when you come down to 0, what is you see, the way we were doing that is certainly not the optimal way. So with the argument I explained to you. But it could be that there are some structural properties of the set, how it looks like if you are coming down to 0. So that it has some. But that this intuition comes more or less from this. Yeah, okay, there are some sources of intuition behind that, but also from the simulations, looking at the simulation. But actually, I would expect that it has some kind of fractal, multi-fractal structures also. That would be very interesting if something of this type is happening.